Hey, good morning, guys. So let's talk a little bit about general structure before we continue to move on with what we're going to talk about this morning. And I do want to let you know today's work is going to be relatively short. You put in a lot of hard work, especially on those transformations this week. We're going to actually split the last part of this objective, this unit in the chapter, down into 2 days, because really you're going to see in a minute, this is going to be easy, but there's just a lot of variations on it. The fourth objective in the chapter is really just about how we apply these exponential functions, which means we're going to be working with formulas. The good news about that is mathematically it doesn't involve a whole lot of brain teasing. You just need to be able to pick out the stuff and put it in the formulas. And of course, while we're gone or we're separated from one another, I'll be providing those formulas for you. So my plan is for us to look at our next quiz on Tuesday, and then the test on Friday. That's a week from today. Excuse me, filming night before. A week from today. So I'm going to show you 2 examples, and your homework today is really only going to deal with some variations on those examples. So don't expect a great many problems at all. So a lot of people have been asking, so where do exponential functions show up in real life? And the simple answer is they show up absolutely everywhere. Anytime we have something that deals with growth or decay, a growth or decay curve, and you're going to hear me talk about where this E is concerned. So we're actually going to come down to a practical use of this E. So if you're interested in finance, if you're interested in social sciences, biology and reproduction, you're going to see these things show up over and over and over again. So I want to let you know in advance that the e-text reading for today, you can actually consider it the e-text reading until the quiz on Tuesday, and it's long, but really it's just a lot of example problems. So I absolutely want you to look at the 2 that I'm going to show you, but what I'm really, like for those of you that are really interested in the mathematics behind this, please take a look at some of the others, because we will look at some variations on this on Monday. So the first example is an example of what we call continuous compound interest. Now, back in the day, when interest was first being applied, say on a daily or a monthly basis, it was a relatively simple thing to apply interest to a principal amount that you might loan someone or that you might have in a bank to earn interest on. But as time has gone on and computers have gotten more and more efficient, we've worked to say, okay, well, what if we cut the time period between when we added interest to an amount by smaller and smaller and smaller and smaller and smaller amounts until we were almost doing it continuously. Not only every second, but every 10th of a second, every 100th of a second, every millionth of a second. What would the result of that be? That's where E as a mathematical powerhouse comes in. If you really look at what it's describing, if we say, okay, 1 plus 1 over n to the nth power, That might not make much sense to you because you might look at it and go, well, how do we know what n is? And the good news is we could really pick any value we wanted for n, but this is going to be moving towards calculus. For those of you that are thinking to go there is, well, what happens to this number as it gets bigger and bigger, as we pick bigger and bigger values for n? Like, for example, 1 plus 1/2 to the second power, or 1.5 squared, that must be a lot smaller than 1 plus 1 million, 1 plus 1 over 1 million to the 1 millionth power. And the simple fact of the matter is, those numbers really aren't that far apart. And the key to understanding it is understanding that n is in both the denominator of this fraction and the power to which this entire thing is raised. So if we think about it, if this is a 2, then we have 1.5. Pretty easy value to understand. We square it, and we get the value of 2.25. Now below what our approximation of e is. But now imagine a number like 1 plus 1 over 1 million. Hopefully everybody can see here, when we had 1/2, we were adding halfway to 2. If that makes sense what I'm saying, I hope it does. In this case, we're adding a very, 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 very small amount to 1. 1 over 1 million. So 1 1/millionth, a very small fraction. So even though we're raising that to the millionth power, we're raising a number that's actually much closer to 1. So as the exponent gets bigger and bigger, the actual base, if you will, once we add everything together inside the fraction gets closer and closer to 1. So as we head towards infinity, which we can't really do, but we can think about it theoretically, we're never really going to get any farther than this number, approximately 2.71828. What I want you to understand, what that number represents is if we could imagine repeating a process as a cycle where the repetition cycle was the smallest unit of time possible. In other words, as close to an infinitely small amount of time as we can get. So that lends itself to what's going on with this continuous compound interest formula. If what I just said made no sense to you, maybe go back and watch it again, and if it still doesn't, here's the meat of the thing. So here's our formula for continuous compound interest, and guys, this part is going to go very fast. This video is pretty close to over. The amount that we're left after a continuous compound interest is equal to P, which is the principal. That's how much we invested. And then up here, we've got two values. The rate of interest, which we're going to state as a decimal, and then the amount of time that that interest has been compounding. And then you can see we have that natural base, E, as part of this formula. So guys, really the trick here is you're looking at the problem. I just want you to practice to be able to get this value in your calculator. That's really what's going on. So with a $6,000 investment at 4.5% interest over a period of 5 years, we plug all those in. We get our final amount is going to be 6,000. There's our investment, our principal, times E raised to the 0.045. Remember, that's 4.5 expressed as a decimal, times 5 to the 5th power, the rate times the time. And that lets us know that after 5 years, we'll have approximately $7,513.94. Now, I've got one more problem to show you that's based on population growth, but since I don't want to waste your time, I'm going to pause for a second while I erase the board and get set up for the next one. So I'll be right back. Okay, so the next example that I want to look at with you is example 12 in the e-text that I asked you to read, and it's about population growth. In other words, how do we measure the population growth of a group or a society? So that formula, which by the way, if you really pay attention, is going to look very familiar to the formula that was just written here, is that P of t, in other words, the population at a given time is equal to P sub O times e to the kt power. Now, don't worry, I'll take you through everything. P sub 0 is whatever our initial population was, T is our time, and K is our relative growth rate stated as a decimal. Now, first thing I want to say is the eagle-eyed among you should recognize that this is essentially the exact same formula as continuous compound interest, just with different variables stated here. But it functions the exact same way. So this is where I want you to understand the power of what E allows us to do. So the problem talks to us about a town whose function to determine their population can be described as 900e times 0.015 times the time. And they want us to find the population at 3 times. Now, first off, if you're good at reading what's going on here, if we know that P sub 0 is our initial population, and they want to know, well, what's the population in 1900, and this town was founded in 1900, then you can just look right at it and go, oh, the population is 900. But I want you to understand why. When we set t equal to 0, in other words, years after 1900, this exponent becomes 0, e to the 0 becomes 1, and 900 times 1 is 900. What about 1950? Well, then all we need to do is plug 50 into our formula. Hopefully everybody can get here that if you can express this relative growth rate as a percent, you could say, you could feel real smart about yourself, that the growth rate in this town is 1.5% per year. So after 50 years, we just put it in the formula, we have an approximate population of 1,905. And in 2012, aka 112 years after the founding of the town, we could predict that the population would be approximately 4,829. I hope everybody can get the math here is not very intense, like in terms of concept. It's really just knowing how to work your calculator. So we're going to split this into 2 parts today and then on Monday. So we're hopefully ready for a quiz on Tuesday. I do want to say one thing. Some of you may be thinking about this, and I've mentioned it many times before. When you look at these applications, especially ones that have to do with population growth or spread, I hope there are those of you out there, depending on how this makes you feel, that can see how this math is at the heart of scientists trying to make determinations about spread of virus and affected populations in the United States right now, based on this exact idea, trying to flatten the curve. And if you've heard that phrase before, flatten the curve in this case is directly referring to the exponential curve of a spread among a population, or the growth in a population, or continuous compounded interest, or anything that grows at an exponential rate. Once again, homework going to be very short today. We're really just going to be working with a couple of these to make sure that you know how to use your calculator. I also hope you have a really great weekend, and I will see you on Monday morning.